Hello, my name is Alysson, and I will present this paper entitled On the Efficiency of Durable State Machine Replication. This is joint work with two master students, Marcel and João, and two colleagues, Nuno and Miguel. Okay? For those of you that don't know exactly what is state machine replication, other common names are Paxos-based or strongly consistent replication. Okay? So in this paper, we will try to see, or we try to investigate what happens when you try to implement durability inside of these replicated systems. And another important thing is that this paper is not only about efficiency, because one of the important goals we have here is how to make it also modular. We want to implement durability, but also in not only in an efficient way, but also in a modular way. Just to remember what's state machine replication, what's a Paxos-based replication. The basic idea is that you have a bunch of servers and some clients, and maybe many more clients. These clients will send requests to these servers, and then these servers will run a kind of protocol, which on abstract way is a total order multicast, but it's basically what implements the Paxos-based agreement. And this protocol ensures that if one server sees and executes that sequence of operation, all the other servers will execute the same sequence of operation, okay? And then, after executing these requests, they send a reply to the clients. In this paper in particular, we want to get this model and modify it a bit, or in such a way that you have, for some of these operations, you are accessing stable storage, okay? And so this is what we call a durable state machine replication, because what we want here is, even if all the machines crash after executing some operation, if the client sees a confirmation of the operation will be on the state after a recovery. This kind of system, or this kind of protocol, or this kind of problem is really important because in many papers or designs, what people do is to assume or to implement Paxos in some of their components to avoid having a single point of failures. Usually this is done on some critical component, okay? One example that's notorious, what I call the coordination service pattern. In general, you have a big data center with a lot of application nodes or nodes running some application, and these nodes coordinate using a small and critical service that implements coordination primitives or stores some very important states such as configuration. So in some sense, Paxos and state machine replication protocols are a kind of critical component of modern internet scale infrastructures. Why durability? I think the answer should be obvious, but sometimes we need to shut down our systems to do some maintenance, and also there are the problem of correlated failures, okay? Bad fortune doesn't respect your upper bound of F faults, so sometimes all your machines can crash, so you need to deal with it, okay? And in fact, correlated failures are more common than what we would expect. These two things are reflected in the design of real systems, okay? Because all the coordination systems that are used in practice implement durability, and the storage systems obviously also implement durability. But the problem here is that in practice, all this implementation, the logic about application, replication, and durability is interleaved in the code, making things very complex to maintain, to design. So this is the kind of code that is really, really complicated to make it right, okay? As can be seen, if you look on the internet and try to figure out, there are not many implementations of these things that you can use. So in this work, we try to implement durable state machine replication in a modular way. By durability, what I mean here is do logging, checkpoint, and state transfer, okay? And the question here is how can you use them without breaking the SMR modularity? Of course, since it appears to be, for maybe some of you, it appears to be more or less an obvious problem, wasn't it already solved, okay? In fact, there are two kinds of works that are very related with this work. One of these, the agreement protocols, there's a lot of papers about how to efficiently order requests and process these messages in strongly consistent replication. We can include here, for example, the longer paper trail about BFT replication, because BFT replication is a kind of, at least in this system community, is a kind of state machine replication, tolerating Byzantine faults. But the problem is that these papers are worried about the normal case execution. So they are not interested in the state transfer protocols, checkpoints, or using disks. They are all interested in the overhead of ordering requests, okay? Synchronizing replicas during the normal operation. So they don't consider disks, they don't consider durability in general, okay? There are some exceptions, but anyway. And the systems, the storage systems or the coordination systems, there are several of them, but what happens is that to make these systems efficient, they are not modular, okay? So everything is done in a more or less interleaved way. So for the remaining of the talk, I'll be first describing some problems when I try to introduce stable storage on the equation of state machine replication, and then I'll go to some proposals of solutions, and finally some evaluation of how our techniques work and solve these problems. Before I describe the problems, let me introduce the model that I'm considering here, okay? I'm assuming that I have n replicas tolerating at most f faults. It doesn't matter if I will be dealing with crash faults or Byzantine faults, because the thing here is that it's completely orthogonal, okay? So I'm talking about state machine replication, and I will not describe the protocols that are used for ordering requests. Then the important thing is that I'm considering a non-synchronous system. It means that it works with quorums. So the system requires n minus f replicas to process requests, to establish an order of a message and process this message. So this is one fundamental characteristics here. In terms of the programming model, the classical state machine model is represented by this slide, okay? On the client side, you have some application that just invoke an operation. Maybe the operation can be serialized as a bunch of bytes. It goes through the network. On the server side, there is a execute up call that calls your service that you implement with some of your code. This service will return a reply, and that's it, okay? So it's in terms of implementation, you implement a method, okay? Of course, this is the classical model. In practice, it's not so beautiful. But if you have durability, you need at least to do some logging and checkpoints at some point. It can be done by the replication layer, by the replication library, or the service code. But if you want to do that on the replication library, which makes the code, the service code a bit less heavyweight, you need at least 2 operations to get snapshots, to serialize the state of the application and give it to the replication library, and the opposite, to receive a snapshot and set it on the application. For the remaining of this presentation and most of the paper, we use a very simple case study, which is a main memory database, okay? So it's a very simple key value database in which all the data fits in memory. It's, for example, the same model that is used in Chubby and Zookeeper, okay? At some point, they are something like this. And given the size of the memory we have these days, this could be used for storing metadata on distributed file systems and things like that. But anyway, the idea here is that you have a simple map interface with put, get, delete, and so on. When you have a read, you access the data from memory and get it to the client. When you have a write, you update the memory, the table on memory, and also the stable storage, which is usually a log, okay? You append the operation on a log, okay? I will show you some problems in trying to implement this on a classical state machine replication model through the key-value store, a very simple key-value store, based on BFT Smart, which is an open source replication library, which is BFT, but it also tolerates crash. So, like I said, the problem of tolerating Byzantine faults or crash faults here is not really relevant, okay? The workload is only writes, because we want to exercise the stable storage. Of course, if I have reads, probably the results will be better, but the reads are served from memory, okay? The point here is to understand what the amount of writes and what the effect of these durability techniques will have on the operation that writes something to the disk. And the state we are considering is a relatively small, 1 gigabyte. So when we try to run this system, doing some writes of 4 kilobytes, okay? If we do everything in memory, like you do the logging in memory without using the stable storage, I'll have this throughput, around 4,700. If I do the same thing using asynchronous disk writes, there will be a small penalty due to the going from application layer to the operating system, but the writes are done on buffer cache, okay? We don't get durability from this. At least not the strong durability that we want. The problem is when we try to do that on synchronous writes, it goes to 63, which is expected because if you process for each operation, you go to and do a synchronous write to the disk, it will be very, very bad, okay? Now the question is, okay, this is a problem, but maybe if you use SSDs, you can solve this problem. This is partially true. If you use SSDs, you improve your throughput a lot, but you are still almost 4 times lower. It's more than 4 times lower than what you have if you have everything in memory. So this is the main problem with using stable logging, and you have to find a way to deal with it, okay? In practice, what most people do, if you want to follow a model similar to state machine replication, is to use asynchronous writes, and maybe you can lose some operations, okay? If you are really, really unlucky. Another option is to use SSDs or non-volatile run, but then you are relying on specialized hardware that may not be available everywhere, especially in a cloud environment, it's more expensive. But anyway, it solves partially the problem. Our idea is to try to get as close as possible to memory. The second problem that we have is when you have checkpoints, okay? So you are putting all your writes on a log, but at some point, you need to control the size of this log for 2 reasons. First, because you want to bound the amount of storage you are using, and second, and most importantly, because you want to bound the time to recover a replica. Because if you have a big log, it will take a lot of time to recover this replica. Maybe for a key value store, it's not really relevant, but the database community already studied this problem and showed that the size of the log is not the problem is the time it takes to replay this log. So the solution is running some periodic snapshots, okay? So in state machine replication, in general, what people do is, okay, for every, 1,000 operations, you stop, take a snapshot, and then proceed, and delete the log, and then proceed. And this is what happens with the throughput of this system, okay? You can see that the first thing you can see here is that there's a lot of perturbation due to the snapshots. The place where I do the snapshot, the checkpoint, are more or less obvious on the graph. First thing you can notice is that the perturbation caused by disk and SSD is more or less the same, okay? The thing here is that we are writing a big bunch of data, 1 gigabyte, so it doesn't matter if the SSD I/O rate is better because it's a bulk write, okay? So the disk bandwidth is good enough to deal with that. The second thing you can notice is that even if I do the checkpoint to the memory, there will be an overhead. There will be some perturbation. And this happens because you have to stop the service, serialize the state, and store it at some place in memory, okay? But maybe it's the overhead of serialization. So how people deal with it, okay? Because, like I said at the beginning, there's a lot of systems that implement some techniques such as durable state machine replication. First thing is copy and write. It's the obvious solution for the problem, okay? The problem of copy and write is that it breaks the model of state machine replication because you have to interleave the code to get the state with the code that execute the operations. The second thing that is used, for example, in Zookeeper is fuzzy snapshots. What Zookeeper does is it stops, it doesn't stop, but it takes the snapshot while you are processing. And it takes the snapshot at random times, okay? This works in Zookeeper because they don't synchronize snapshots with logging because they have idempotent operations, sorry. The point here is that even if when recovering a replica, you have an operation on the log, and on the checkpoint, it's not a problem because you can execute the operation twice or 3 or how many times you want. The final state will be the same, okay? But of course, to make these 2 things work well, you need more than 1 stable storage, okay? You need 2 disks, for example. One to do the logging and another one to create the checkpoints. The third problem is related with state transfer, okay? I have these replicas, for example, running Paxos, and at some point one of them crashes and later on recovers, okay? During the crash there are no problems because we tolerate a single fault here because we need a quorum of 2 replicas to process requests. But when this replica recovers, it will ask for state, and then one of the replicas that are needed for processing requests will have to use its resource to send the state to the recovered replicas. And the effect will be somewhat devastating, okay? So what happens here is that the system continues processing. It's different from the checkpoint because the system doesn't stop, but you are using the resources of the replica to send the state to the recovering replica. How people solve it? As far as I know, there are two ways to solve this problem with the standard state transfer protocols. First one is to have additional replicas. Maybe that's one of the reasons why people on Zookeeper use it with 5 machines and not 3, to tolerate 2 replicas, not only because they want to tolerate two faults, but because they want to avoid, to have some spare replicas to deal with certain cases like this. Another way to deal with the problem is to avoid answering. If your system is under stress, you don't help the recovering replica, okay? But then, if another replica crashes, you may have problems, okay? Because you are delaying the recovery, and you are delaying fault tolerance. Okay, so these are the basic problems. Like I say, they are solved. Most people solve them in practice, but the problem is that the way they solve it is based on making the code even more complex than what it already is, okay? These protocols are already very complex and people deal with them, integrate things inside of them to make them even more complex, but efficient. We propose a set of solutions to solve the problem without changing the state machine model. So my final goal is to have the service code will only implement execute, get state, and set state, and that's it, okay? Don't worry about copy and write and all of these things. And I want to use the state machine protocols, the ordering protocol, as they are. Okay, so we propose the 3 new techniques. Most of them are very similar to things that people from database community or file system use, but the point here is to take into account the particularities of the state machine replication model, okay? The first technique is parallel logging. The point here is try to make logging a bit more efficient, okay? The solution is based on 2 observations. The first one is that I can send a message to the reply to the client only after the operation is executed in memory and also in the disk, is logged in the disk, okay? And the second observation is that the disk bandwidth, and I don't know how much it works, it's valid for SSDs, but it's very good. So if I write a lot of data at the same time, it will be much better than doing several writes, small writes, okay? This is more or less well known. So what we do, we have this agreement layer that keeps ordering requests, assuming that you have a lot of clients trying to write things. So we will batch these requests, we will enqueue them, and at some point when the upper layer, the application, is free, we give the batch to a thread to write it on the log, and to another thread to execute the operations, okay? So these 2 threads will run in parallel. Remember that the state machine should work only on memory or on a separate disks. And then what will happen is that, in the end, the 2 things will when these two threads finish processing this batch, I can reply to the clients, to all the clients that had message operations in these batches. So the idea is more or less simple, but you see that it works very well. The second problem is checkpoint, okay? So the main problem of checkpoints is that people that do state machine replication do checkpoints in a synchronized way, okay? Because it makes sense to do that in that way because you have several copies of the same checkpoint. So if you want to recover if there's some data corruptions, it's very easy to get other checkpoints, okay? To design protocols to validate these checkpoints and things like that. So what we want to do something called sequential checkpoints. So we schedule the checkpoints and the replicas execute checkpoint one after another. The problem with it is that it will make the state transfer much more complicated, okay? But the basic idea is to do that, is to do checkpoints I stop replicas at different points in their execution to create different checkpoints. The final solution is called collaborative state transfer, okay? The basic idea here is to deal with this problem of having checkpoints. I created a problem, basically, to solve the problem of synchronized checkpoints, I created a problem for state transfer, okay? Now I need to solve it. If I'm assuming that no validation is required, there's no problem at all, okay? I can ask one of the replicas, probably the one that did the checkpoint most recently, and get the state and the log. Note that now probably I will have always a small log to reply because I have several replicas doing checkpoints in different points, okay? But if I need validation, which is the Byzantine case, okay, maybe the state is corrupted, it's a bit more complicated. I will not talk about it because our chairs say that we don't need BFT here, but seriously, it's more complex, but you can see the details on the paper. But the point here is, even if I solve this problem, let's go back to this slide. If I solve this problem, I'm still using one of the replicas, okay? I'm still making the quorum. I don't have the quorum. In this case, I have 3 replicas. One is recovering, one is sending the state, which is the part in blue, and the third replica is not enough to process. I'm still having problems here if I want to tolerate a single fault, okay? So there's an important optimization for dealing with systems that tolerate a single fault, which is, instead of asking all the state, and by state I mean the checkpoint and the logs, to a single replica, I spread the load of sending state to several of the replicas, okay? So one of them will send the checkpoint, another 2 will send different parts of the log. This example is for the Byzantine case when you have 4 replicas. You have a 4th replica that is asking the blue parts. The parts in white in this figure B are digests that I need to validate the state, okay? Anyway, let's see how this works in practice, okay? So, like I said, we implemented this on this BFT Smart replication library. It's for BFT, but right now there's already some experimental support for crash fault tolerance, which is the opposite. So it was designed first for BFT, and now it's supporting CFT only. But the basic idea here is that we modified the system to make a layer that can deal only with durability, okay? This same design can be applied in any system that we implement state machine replication. This durability layer implements the 2 threads that we need. It do the checkpoints, logging, and so on. What's really important here is that you can see that on the service, from the point of view of service, you are still implementing only execute, get state, and set state, okay? We developed 2 very simple services. The first one is very simple, the second one is not so. Using this library, which is called DuraSmart. So we implement the key value store. As you may imagine, it's a very, very simple system because we are getting the durability for free. We are getting the consistency for free. So we just need to use like a hash map, no, a tree map on Java and implement it on this service, okay? And we also implemented a coordination service, but we discussed this, it's based on an old service that we proposed in 2008. In this case, we make it durable, okay? But I will not show this. If you want details, go see the paper or talk to me later. The environment, we have a good machine with good disks, SSD and normal disks, good network, 4 servers, more than 1,000 clients. 1,000 clients are threads on these servers, on some machines of our cluster. We run workloads of write only, okay? And the state is around 1 gigabyte. In the paper, we discuss some variations of this setup, but I think for getting the problem is more or less the same thing, okay? Okay, parallel logging. In this graph, you can see the same results I already showed you, okay? When I use a naive implementation, respecting the model of state machine replication, you do 63 writes per second on disks, bit more than 1,000 on SSD, and more than 4,700 on memory, okay? Now, what happens when you put parallel logging? This is what happens, okay? Because we are stressing the system to the most we can achieve in our environment. What we are having here is parallel logging allows your system to have a performance as close as a pure memory system, at least in terms of logging, okay? First thing that's important here is what I already said. Second thing is that if you look at the comparison between disks and SSD, you'll see that disks present a bit better throughput than SSD, and our solution running over SSD. And this happens because the throughput for the size of the record we are writing to the disk, or to the stable storage in this case, on the disk is a bit better than, it's 4 megabytes more or less. Each write to the disk is around 4 megabytes. Remember, each request is 4 kilobytes, so we put a bunch of them on this peak throughput execution. And of course, when you use SSD, your latency is much better. Okay, there's a price to pay in using disks, and we can't avoid it. If you really want durability, okay? Then there's the problem of sequential checkpoints. As you saw before, you have this perturbation when the replicas stop. So what we try to do is this, do the checkpoints in different points of time. And what will happen is something like this, okay? We have two executions here, one under a high load and another one is with a medium load, okay? So you are still writing things. What happens is that under high load, there is no blocking. The system never stops, okay? In fact, it may stop a bit, but you know, our measurement doesn't get this amount of seconds in which it stops, okay? And it stops, no. It's perturbed. There's some perturbation yet because of lagging replicas. Because you have the quorum, and when you run this kind of protocols, there's always some replicas that go in front of the others, okay? But if one of these replicas stops to take the checkpoint, one of the lagging replicas needs to keep up with them and participate on the agreements. And this causes this problem here. But if you have a medium load or a low load in terms of writes, this problem never happens because there's always before executing a request, there's always time for these lagging replicas to keep up with the remaining of the system. But this is an interesting phenomenon that happens with this kind of protocol. And if you are interested in discussing it, you can ask me later. And finally, I want to illustrate what happens when you try to use the collaborative state transfer, okay? In this case, we are assuming one fault, f equals 1, with state validation, okay? So in the normal case, it happens with the case that happens, for example, in all BFT protocols, okay, all BFT state machine replication protocols, you have something like this. One of the replicas send the state and the log, okay, and the others will send a digest of this information. In crash fault tolerance, in a normal Paxos, in general, you ask for the state for the leader, for example, and then you have this kind of problem. So the problem is very similar, okay? When we try to use collaborative state transfer, which in this case is this, okay, we try to spread the load among several replicas, you can see that there's a lot of perturbation, but we are still processing, we have less problems, or let me put that in a better way. We have less problems than if you will want to get all the state from a single replica, okay? You can see on the blue area that this is more or less what happens in terms of with the throughput when I get this part of the state from the other replicas. And this is interesting to see that you can look on the two areas there, and you can see that the blue area is around 1/3 of the red area, okay? And this happens because in this particular execution, what we are trying to do is get parts of the log that are more or less of the same size of the checkpoints, okay? So each replica is sending 1/3 of what is sent in the usual state transfer. But the final thing here is that in the usual state transfer protocol, in which you ask the state for a single replica, you get 24% of the normal throughput during the state transfer. In this execution, okay, it varies a lot. But by design, it's always better to ask the state from different replicas. Of course, the protocol is more complex, but then you have up to 60% of the normal throughput during state transfer. So in summary, so durable state machine replication is a fundamental technique for critical services. It's a complex and difficult to get right. If you ask anyone that worked with these kind of things, they will say that it's very hard to make it work and have some stable code. Our contribution here is a principal way to deal with this problem, okay? Without breaking the beautiful state machine replication model, which is having this execute operation. Only this execution operation. So introduced 3 techniques, and if you are interested, the code is available on the internet, and that's it. Thank you.
Hi, I have a caveat, and that's that you need some kind of state, how to put it? You need some kind of state containment so that you don't have state leakage across fault domains or across replicas. Otherwise, you need perfect fail-fast, and there is no perfect fail-fast. So what this does is it changes the number of replicas you need. So I think it's a caveat of your state management that you have to have some sort of state isolation. Second point is that the parallel logging, what we found at Tandem is when you do parallel logging, is you have to have another log so that after you do a flush of those logs, you do the flush of the root log, and then you have sort of atomicity across all of them.
I'm not sure if I understood your comments. In this particular implementation, we have only a single log.
Ah, okay. You
So
said parallel
it's a
logging.
single log, and then we write things there. After writing the checkpoint, we delete this log.
Ah, okay. All right.
Okay. So
But as far as the state containment?
I don't think I understand what you told me. In fact, what
In
I
other
mean by state.
In other words, by the time you notice that there's a failure, in other words, your fail-fast says by the time you notice you've got a failure, your state has leaked across failure domains or across replicas, in which case you don't know how far you have to go back.
Okay. The point here is that, first thing is that in these protocols in general, you don't notice that you have a failure, because they are asynchronous. I mean, as long as you have a quorum, you keep working. The only thing that you need to detect is the leader. There's a leader that establishes orders for these requests. The failures I'm considering here.
How do you ever have a failure if you don't notice you have a failure? I mean, something has to be failing.
No, you can do that, but it's maybe outside of the system. Yeah.
Right.
But the state machine replication model itself doesn't require that you have some detection of failures. Only for the leader. But I think we can talk about it offline, because I didn't understand exactly what you.